Welcome back, everyone. In this video, we're going to be talking about arrays. And to understand arrays, we first need to understand this. This is a stick of RAM, or random access memory, that you'll find in every desktop, laptop, mobile phone, and many other devices. More specifically, this is a memory module, and these will come in different sizes and shapes depending on the device that they're designed for, as well as different capacities, such as 1 gigabyte, 2 gigabyte. Nowadays, it's not uncommon to see 8 gigabytes, 16 gigabytes, or even 32 gigabyte sticks of RAM. And on these sticks of RAM, you'll see these smaller chips. And these chips contain the actual transistors that we use to represent the bits in our computer's memory. Maybe this is a 1 gigabyte stick of RAM, and we have 1 gigabyte or a billion bytes. Maybe we have 2 gigabytes or 2 billion bytes. It depends on the physical chip, but suffice it to say, we have some finite number of bytes physically implemented in this chip via transistors. And we can start to think of these bytes as being a grid of bytes. And it would stand to reason that we could number these. For example, we could start counting at 0 and say that this is the 0th byte. And then the next one would be the first byte, and the second, and so on, all the way up to byte 1 billion or 2 billion, whatever the size stick of RAM this is. So why is this relevant? Well, we've already saw the use of variables, and I propose that each different data type uses some number of bytes to represent it. We saw that chars, or characters, used 1 byte, ints used 4 bytes, and so on. And then we saw strings down here at the bottom that take up a variable number of bytes. Again, it's going to depend on the length of the string to determine how many bytes it's going to use. So when we create a variable in our code, like this char grade variable that has the value a, that a might literally be stored up here in this first byte of memory. And we'll abstract this hardware away and blow this grid of memory up so that we can see this better. But this byte of memory may literally have the value a, like this. Now, generally, you won't really care where physically this char is, but suffice it to say that it will be stored at one of these memory locations. And again, a char uses 1 byte, and it's important to understand that it will be stored in one of these single bytes. If we used an int, on the other hand, say int age is equal to 21, it might look like this, and it would give us 4 bytes, contiguous. In other words, all 4 bytes would be back to back to back. If we used a long, which is 8 bytes, it would use all 8 bytes in our computer's memory. And we just use this memory like a canvas, where we can store data in units of bytes, or 8 bits. And when we think about the memory in our computers, it's reasonable to think of it not as physical chips and transistors, but rather just this grid of bytes that we can use to store information and data. So let's see some examples of this. I'll jump over to my Ubuntu virtual machine, and I'll start by opening the terminal. We'll change directory into tutorials and use code dot to open up VS Code. I'm going to have to close out of this, and I'll save this. And now I'll create a new file, and we'll call this arrays.c. And I'll do my normal boilerplate, hash include stdio.h int main void curly brackets return 0. And now let's just define some variables. We'll say int score1 is equal to 72, int score2 is equal to 69, and int score3 is equal to 89. And maybe these are some scores for a game that we want to keep track of or something along those lines. And now if we think about what's going on in the computer's memory, we can bring back this grid. And we can think of this int score1 is equal to 72 as literally storing the value 72 in these first 4 bytes. And again, it's not really important where this 72 is being stored, just that it is taking up 4 of these boxes, or 4 bytes. Score 2 will probably end up next to it in memory. Although this isn't always the case, there's a chance that if we have other stuff going on in our program, that these variables might be separated. They might end up here, or they might end up here, or anywhere else randomly in this memory. To keep our example simple, we'll suppose they all ended up at the top. And finally, score 3 or 89 might end up right here. Now, if we were able to physically look at the transistors in this stick of RAM, we would see the binary representation of these numbers. And from this point forward, we're not really going to have to think at this binary level. It suffices to think about these numbers in their decimal equivalent. Now, if we come look at this code, it might be jumping out to you why, but this probably isn't the best design, right? We have these 3 lines of code that are basically the same, except for this arbitrary value at the end. And while it's not a huge deal with 3 values, what if we had 10, or 20, or 50 different scores? Well, then we're going to have 50 different lines of code that are all basically the same. And this is where arrays are going to come into play. Arrays are a way of storing more than one piece of data in our computer's memory under one variable. And arrays will guarantee to use memory that is contiguous, or back-to-back. Because of the fact that the memory is contiguous, or back-to-back, we can easily access each individual member of an array. So instead of defining these 3 different variables that all look pretty much the same, let's see how we can define an array. And to do this, we would say int scores, plural, with square brackets. And then inside these square brackets, we need to tell the compiler how big this array should be. And if we want to store 3 scores in this array, we need to put 3 right here. And this is like telling the compiler, give me a variable called scores that is an array of size 3, each of which will be an integer. In other words, this is how you declare an array that has enough room to store 3 integers. And the compiler will ensure that there are 12 bytes contiguous, or back-to-back-to-back, in your computer's memory that you can use to store some values. And the fact that these bytes are contiguous will be very useful in just a minute. Why 12 bytes though? Well, because ints use 4 bytes, and we want enough room to store 3 of them, or a total of 12 bytes. And now we can start to store some values in this array. We can use scores, and then these square brackets again, and bracket 0 to get to the first location in this array. And again, we start counting at 0 in programming. So 0 is the first location. And these locations are often called indexes. When we use scores bracket 0, we're saying go to the first index in this array, and then we're going to store the value 72. We can then go to the second index with scores bracket 1, and we'll assign the value 69. And finally, we can go to scores bracket 2 and assign the value 89. And I know that this syntax is a little different, so let's go over this again. On this first line, line 6, we're declaring an array of 3 integers. If we want to go to the first location or the first index of this array, we use these square brackets, and we go to scores bracket 0. We can then assign the value of 72 to this location. Then with scores bracket 1, we can go to the next location in this array, and we can assign the value 69. And finally, we use scores bracket 2 to go to the final location and store the value 89. So we're creating an array of size 3, and we're inserting 3 values into this array. And one of the upsides now is that we only have this one variable called scores that keeps track of all of our scores. And yes, you still have to go into the array or index into each location at this array using these square brackets to assign a value or to get at individual values. But at least now we don't have to declare a separate variable for each value. And as a side note, we'll see in the next video a shorthand to this so that we can do all of this on one line if we already know the values that we want to put in this array. More on that in the next video. And we can perform operations on these values just like we would if they were variables themselves. For example, let's just make this program do something simple. Like let's just add up these three values and print them to the screen. So we can use printf. Let's just say sum of scores. And we're going to use our %i placeholder followed by a new line. And then we're going to pass this second argument of scores bracket 0 plus scores bracket 1 plus scores bracket 2. And this is fine. We can perform these math operations right here as our second argument to printf. I'll make sure and put my semicolon at the end. I'll save this and let's open up the terminal. We'll compile this with gcc -o arrays.c. And if I run this with /arrays, we can see that it adds up these three numbers and we indeed get 230. But it's kind of stupid that I've hard-coded these three scores in here because this program will only calculate the total of these three scores. So why don't I go ahead and prompt the user for these three scores instead? To do so, I can come up here and include the CS50 header file so that I have access to the function getInt. And instead of hard-coding 72, let's call getInt, prompt the user for something like score. And then we'll just copy this for scores bracket 1 and for scores bracket 2 as well. And if I save this, and we'll come recompile. However, this time, since we're using the CS50 header file, we also have to give the -l CS50 argument, and we'll hit enter. We get no errors. Let's say /arrays to run this. And for the first score, let's just give 72. The second score will give 69, and the final score will give 89. And you can see that this is still working for these three values. Let's run this again, and we'll just do something simple like 1, 2, and 3, and hopefully we get 6, and we do. But hopefully it's jumping out to you that this isn't particularly well designed, because we have these three lines of code that are basically the same, except for the location in the array. And the solution to this is often a loop. So let me do this. I'll still create my array of ints of size 3, and then I'll run a loop. I can say for int I is equal to 0, I is less than 3, I++. Then in here, I know this is going to look strange, but what if I did scores bracket I is equal to getInt, and we'll prompt the user for a score. So let's break this down. The loop is nothing new. We're going to be doing something 3 times, which is the same size as our array. And so on the first iteration of this loop, we want to prompt the user for a score, and where are we going to store it? Well, the first iteration of this loop, I will be equal to 0. So we're going to store whatever the user enters into scores bracket 0. On the next iteration, I will be equal to 1, and we'll be again prompting the user for another score and storing it at scores bracket 1. And then finally, on the last iteration, I will be equal to 2, so we'll go to scores bracket 2 and store the value that the user enters. And now this is a little better designed because we're looping 3 times and then prompting the user for that score. And then we're storing that value into each of the locations in this array. So now let's think about what's actually going on in the computer's memory. And it's pretty much the same. However, instead of having the individual values of score 1, score 2, and score 3, now we have a single variable. It's an array called scores, but we can index into each of its 3 locations by using scores bracket 0, scores bracket 1, and scores bracket 2. And the key here is that the memory is contiguous. Remember, when we were using regular variables like score 1, score 2, and score 3, I said that they'll usually end up right next to each other. But there is a chance that for whatever reason, score 2 ends up down here, and score 3 ends up down here. By using an array, we are guaranteed to get these 3 values back to back to back. And this is why we can easily index into the array's locations using these square brackets, since the next index of the array will be some exact number of bytes away. So this is how we create arrays, and the true power of arrays might not be completely apparent yet, but over time will we see more examples of these and why they're so useful. We've seen this example of an array of integers, but we can also create arrays of other data types as well, such as floats, doubles, chars, strings, and later we'll see how we can even have arrays of arrays, and how we can really build out these different data structures or structures in our computer's memory to better organize our data. But before we wrap this video up, I want to show you one last thing. We've seen how we can pass variables to functions as inputs or arguments, and it's worth noting that we can also pass arrays as arguments to functions. Let's suppose that we want to create a function called sum of scores that's going to take a scores array as input and return to us the sum of those scores. We can come down here outside of main, and this sum of scores function is going to return the sum of a bunch of integers. And if you think about it, anytime we add integers together, we're going to get an integer as the solution. So this function should return an int. We'll call it sum of scores, just to be descriptive. And the inputs to this function are going to be an array of integers. And the way we would tell the compiler that this function is to take not just an integer, but an array of integers, is we would first say int, and then give this a name. Let's call it array, just to be clear that this function expects an array, but the key here is these square brackets after the name of the variable. And this is saying that I want this function to take an array of integers as input. So this is how we would declare a function called sum of scores that returns an integer and takes an input that is an array of integers. The square brackets being the key difference. And now we can implement this function. Well, what do we want to do? We want to return the sum of all the values in this array. We know that the array has 3 values. So we can use this keyword return, and we want to return array bracket 0 plus array bracket 1 plus array bracket 2, and this with a semicolon. And now if we just copy this function prototype right above main, end it with a semicolon, and now we can use this sum of scores function inside our main function. So I can come down here and I can call sum of scores and pass to it our scores array. And I can assign this to a variable called sum, for example. And now down here in printf, instead of doing this addition manually, I can just pass the sum. And if we save this, we can come back in here, recompile, rerun. Let's give a score of 1, 2, and 3, and we see this is still working as expected. But I think we can design this a little bit better. If you look on these highlighted lines, what up here has been repeated in both of these? Well, this number 3, which is the size of the array, and we're using that number down here in our loop also. And anytime you see this, it should kind of jump out at you. Why? Well, because eventually you or someone else looking at this code might just happen to change the size of this array to 4. And you're not going to know that magically this number down here also needs to be changed to a 4. And this is what's called a magic number. It's just some number that appears magically, and it's up to you to know that if you change it here, you also have to change it down here. So what might be the solution to this? Well, I would argue that we could store this in a variable. And even better, we could use a constant variable, like we did in a previous example, so that this number can't be changed anywhere in our code. So I can come up here outside of main, right above it, and I can declare a const int, and let's give this the name size. And since this is a constant variable, our variable name should be all uppercase, and we'll just give this the value 3. And now down here in scores, instead of passing 4 directly, we'll pass size, and we'll also come pass size in our for loop. Now, if we ever want to change this to support 4 scores or 5 scores, we just change this one value and we're done. But now down here, I think we may have broke our function. Because right now, this function will only add up 3 values from an array. And we could fix this, of course, by adding plus array bracket 3 if we wanted to support another value. But we want this function to be able to take an array of any size and return the sum of all the values. And the solution to this, of course, is a loop. Let me erase all of this. And first I'll start by initializing a variable called sum, and we'll just set it to 0. And we'll see why here in a second. Now we can run a loop. We can say for int I is equal to 0, I is less than size, I++, and now down here in my curly brackets, we want to add the current sum to whatever is at array bracket I. And we want to store this back into the sum variable. And I know this might look strange, but we'll break this down in a second. Now I can come down here outside of my for loop, and I can just return the sum. So what is this doing? Well, first we're going to initialize this variable called sum to 0, so that we can keep track of the sum each time we iterate over this loop. And then we're going to start this loop. We initialize our counter of I to 0, and we check if I is less than the size variable, which in this case is 3. Since 0 less than 3 is true, we're going to run this code down here. And what is this doing? We're taking whatever the sum is, right now it's 0 of course, and we're adding to it the value at array bracket I. Again, I is 0 on this first iteration, so really we're getting the value at array bracket 0, or the first value in the array, and we're adding it to this sum variable. And we're assigning that back into this sum variable. Let's suppose that we passed this scores array to this function as input. On the first iteration, array bracket 0 will be our 72. So when this first iteration completes, the sum will be 72. And then we increment I to 1. And we'll check again. Is 1 less than 3 this time? And again, that's true. So we'll run this code. We'll add sum, which is 72 at this point, to array bracket I. This time, I is equal to 1. So we're going to the array's first location. And we'll find the value 69. So we'll add 72 plus 69, which is 144, and we'll store that value in sum. Then we increment I to 2, and we check again. Is 2 less than 3? And of course, this is still true. So we run the code, we add sum, which is now 141, to array bracket I. I is now 2. So we're going into the array's second index, and we're going to find the value 89. So we add 141 and 89 and store the result, which is 230, into the sum variable. Finally, we increment I to 3, and we check the condition, is 3 less than 3, and this will evaluate to false. So we exit our loop, and then finally, we will return whatever this sum variable is. In this case, it would be 230. And like this escalated very quickly. This function just got a whole lot more complicated. However, now it's better designed because it's dynamic. We can pass an array of integers of any size to this function, and it's going to sum up all the values. And slight optimization here. If you remember, we have this plus equals operator, or our syntactic sugar that we can use right here. Instead of saying sum is equal to sum plus array bracket I, we can say sum plus equals array bracket I, and this is going to perform the same operation. And I know that this final example might have been confusing, but the main takeaway here is the syntax we're using up here to pass an array as an argument to this function. And this video is getting a little lengthy and a little dense, so I don't want to throw more at you all at once. But one final thing that I think I should mention is that in C, once you pass an array to a function, there's no way of knowing the size of that array. So it's typically the case that we should pass the size as a separate argument to this function. And what I mean by that is that instead of this function just taking an array as input, let me also declare another argument called length. And now instead of passing size right here, we're going to pass length. And up here, we also need to change our prototype. So we say int length. And now when we call this function, instead of just passing the array scores to it, we're also going to pass the size, which is going to come in here and be our length. And this is very subtle, but it's just an example of how we can pass the size of an array and the array itself to the function, so that it kind of stands on its own and doesn't depend on this constant size variable up here. So let's go ahead and end this video here because I know this has been a lot and probably the most complicated syntax that we've seen thus far. I really hope if there's any questions, you don't hesitate to ask them in the comments. As of right now, I have alerts set up for when I get comments on my videos so that I can respond as soon as possible. In the next video, we're going to see how we can use arrays of other data types as well and get more practice with this powerful concept of arrays. I want to thank you all so much for watching. I hope this wasn't too confusing, but if it was, just stick with it. the more you work with the syntax and these arrays, will they start to feel more and more familiar. I appreciate all your support, and I hope to see you in the next one.